Hello class, this is Mr. Bufey. We are moving on. We are moving on to factoring. When a is greater than 1, and when we say a, we're talking about the quadratic function. Here you can see where my cursor is. A x squared plus bx plus c, so we're talking about that a. So we're looking at quadratic functions where a is greater than 1, and we no longer can factor out a GCF, or a greatest common factor, that will allow a to equal 1. So we're going to learn how we factor a quadratic function when we can no longer factor out a greatest common factor such that we allow a to equal 1. This is the most general condition where we can't factor out anything, and the a is going to actually be greater than 1. So there's a method for factoring the quadratic function when a is greater than 1, and that's what we'll do. But the first thing we want to do is review in these two little sentences here what we've done already. And the first thing we did with factoring was we factored quadratic functions when a is equal to 1. So this is a quadratic function, ax squared plus bx plus c, and we learned how to factor quadratic functions when a was equal to 1. And when a is always equal to 1, we no longer have to have the a there, and we just have x squared plus bx plus c. And when we had equations like that, which, b could be 10 and c could be, 15 or something, where you have x squared plus 10x plus 15. Okay, so when we had equations like that where a is equal to 1 and we had a number for b and a number for c, our factored solution always looked like this. We start off with an equation x squared plus bx plus c. Again, b could be 10, c could be 15. Then our solution would be x plus g times x plus h, where we would have to find g and h such that g times h would equal c and g plus h would equal b. Okay, and so that's pretty much how we would find the factors of a quadratic function when a is equal to 1. Again, the factored solution would be x plus g times x plus h, and we find g and h by finding a g and h such that g times h equals c, and g plus h would equal b. So when we found a g times h that equaled the c value here, and a g plus h which equaled the b value here, we stuck that g and h in here, and we were done. So that's how you factor a quadratic function, which is a trinomial, into the product of two binomials. Okay? Now, after we did this, we said, what about those quadratic functions when a is greater than 1, but we could factor out a greatest common factor so that a would, in effect, a would go back to 1. And remember, we said how we do that is whatever number was in front of x squared, if we took that number, which might be a here, and divided it by each of the numbers in this term, if it could divide evenly into each of these terms, then we could pull that GCF out, and it would leave us with a 1 in front of x squared, and then we would have bx plus c. And so the only difference between the process with step 1 and the process with step 2 is that we would have to factor out that GCF. Once we factored out the GCF, the way to factor this quadratic function is again to find x plus g times x plus h, where g times h equaled this c and g plus h equaled this b. But after we found x plus g and after we found g and h and plugged them back in here, you have to remember to multiply times the GCF, because without that GCF, we won't be able to get back to our original equation. We'll just get back to this equation here. So the process for finding our factored solutions is pretty close in these two conditions. The only difference in process number 2 is we have to factor out a GCF. Once we factor out that GCF, we use this quadratic function to find the g and h values here. And again, to find the g and h values here, g times h has to equal c and g plus h has to equal b. Once we find the GH's that where their product is equal to c and their sum is equal to b, we put the g and h in here, and then we go back and get this GCF, multiply this GCF times these two, and that's our factored solution. Okay, but now we have a situation where a is greater than 1 and we cannot factor out GCF. Okay, and what that means is when we have numbers in our quadratic equation, ax squared plus bx plus c, when that a value is a number that can't be evenly divided into b or c, then we can't factor it out. Okay, and there's lots of equations that are like that, where there's an a value or a number in front of x squared such that when you divide it into b and divide it into c, it won't divide evenly, and therefore we can't pull it out. So how do we factor a quadratic function when you can't pull out a GCF and that a value stays greater than 1? That's what we're going to describe next. That's our next section. That's what we're going to do now, and that's what I'm going to describe here next. So when we can't factor out that a, and that a is going to be greater than 1 and it's going to stay there, here is how we go about factoring our quadratic function. And what it's going to look like when we're finished, I forgot to mention this up here, when we're finished, we're going to start off with ax squared plus bx plus c, and when we're finished, we're going to have two binomials. Remember, this is a trinomial. It has 3 terms, ax squared plus bx plus c. When we're finished, we're going to have 2 binomials. That's 2 expressions that only have 2 terms, and it's the product or the multiplication of these 2 that will equal this. What you'll see that's different about our solution here is now we're going to have numbers in front of x. Before, in these 2 other methods, we never had a number in front of x. We only had to worry about g and h. See, g and h. We never had a number in front of x. But in our new solution, when we can't factor out, when a is going to stay greater than 1, then that means in our solution now we'll still have 2 binomial expressions such that when they're multiplied together, they're going to equal ax squared plus bx plus c. But now we're going to have numbers in front of x in our binomial expressions. Previously, we only had 1s in front of x in our binomial expressions. And so that's the primary difference. Okay? right, so let's see how we get there. So let's start off with seeing how we find G and H, and how we use G and H differently when we have a greater than 1. So if we have a quadratic function, ax squared plus bx plus c, when a is greater than 1 and no GCF can be factored out of the equation, then we still have to use the quadratic function spreadsheet to find G and H. But the way that we find G and H is just slightly different. Slightly different. And again, you don't have to use the spreadsheet, but if you don't like keeping a lot of those numbers in your head, then the spreadsheet's the best way to go. Everyone can't be like Darius Kane. Okay, Darius, that's a shout out to you. Okay, so here's how we find G and H. And so the big difference here is to find the product of G and H, or G times H. Previously, we would say G times H is equal to C. But this time we're saying G times H is equal to A times C. So whatever number is represented by A, which is the number that's in front of x squared, and whatever number is represented by C, which is the third term in the quadratic function, we need to multiply those two together, A and C, and then whatever that number is, the product or the multiplication of G times H has to be equal to A times C. Again, previously it was just C equal to G times H. Now we have A times C is equal to G times H. What stays the same, however, is that the sum of G and H will equal B, and B is the middle term of our quadratic expression. And so what we do from here is we go into our quadratic function spreadsheet, and we look for values of G and H such that when we multiply G and H together, they will give us the number that's equal to A times C, and at the same time that same G and H must sum to whatever B is. Okay, so once we get those numbers, we're going to do something different. Remember, in the previous two methods, once we got G and H, we just stuck G and H into these expressions, and we were done. Right? So we get G and H, we stick it in here, and we're done. Even with the second method, when we had to factor out a GCF, we would stick G and H in here, and we were done. But with this method, once we find G and H, we're going to use G and H to rewrite our quadratic function so that we break the bx, or the middle term, up into two different numbers. Okay? So what we have here is, once we find G and H, we're going to take the G and put an X on it, and take the HX and put an X on it, and we're going to replace the BX with GX plus HX. And then we're going to take the AX and put it on this end, and take the C and put it on that end. Okay? So when we get down to the examples, you'll see how this works. I'm just sort of summarizing what we're going to do. Okay? And so the purpose for this is, once we've rearranged the quadratic function so that we replace bx with gx plus hx, what we're going to do then is rearrange the equation into two expressions, where we take the gx term and we're going to group it with the ax squared term. Then we're going to take the hx term and group it with the c term. So we're really not changing the equation. We're just grouping it so that we're taking the hx and the c and we're putting parentheses around them and calling that one expression. Then we're taking the ax squared and the gx and we're putting them together. So you can see that here in step 3. In step 3, we just bring down what we had up here, ax squared plus gx plus hx plus c. And remember, we had bx here, but we replaced bx with we replaced bx, as you can see right here, we replaced bx with gx plus hx. And remember, we got the g and the h from here. We went to the quadratic function spreadsheet, found g and h. Once we found g and h, we put an x on g and an x on h, and we're going to replace the bx with gx plus hx. So we do that, and then we group the hx with c, and we group the gx with ax squared. And we do that just by putting parentheses around ax squared plus gx, and then we put parentheses around hx plus c. Okay. Then in step 4, what we're going to do is factor out a greatest common factor from each of these terms that have parentheses around them. Okay. It's not going to make a lot of sense when you look at it here. When we get to some numbers, you will see that. But what we'll do is we go from this term here, where we have ax squared plus gx, and then we have hx plus c. What we're going to do is factor out a greatest common factor from each of these, so that we get our expression looking like this. Now, just looking at this, there's no way for you to understand that. So I know it's a little confusing now, but when we go down below and get some numbers and put some numbers in, you'll be able to see exactly what that looks like. Okay? One of the reasons that we're doing this is so that we can use the reverse distributive process to actually find our solution. Okay, and so the reverse distributive process is described here. And again, just sort of follow along with me. I know I've sort of left you and you're a little confused right now, and you should be, because when I put in symbols here, it's hard to follow along. Okay, but just bear with me, and when we get to the numbers, you'll sort of see. So here in 5, we're going to use the reverse distributive method to show you how we're going to get our solution. So the reverse distributive method works like this. If you have a number such as m, and if m is multiplied by b, and if you have another number which is a, and it's multiplied by b, then what you could do, you could actually pull that b out of this expression, put a parentheses around m and a, and then multiply that b times m plus a. Okay, so that's the reverse distributive process. Okay, again, the reverse distributive process looks like this. If you have a number m that's multiplied by b, and if you have a number a that's multiplied by b, so you got these two numbers, m that's multiplied by b and a that's multiplied by b. What you can do is pull that b out of that expression. See, we're pulling the b out. And you can pull it out because the b is common to both of these terms. B is multiplied by m and b is multiplied by a. So if we pull b out, you can see that if we multiply b times this expression, b would be multiplied by m, and b would be multiplied by a. Okay, so this is the reverse distributive process, because when you look at this expression, b is distributed with m, and b is distributed with a. What we're going to do is pull b out so that b is not distributed across m and a. B is on the outside of a, but it's still multiplied. And so it's the same, because if you multiply b times the parentheses m plus a, b will distribute across both m and a. And that's called the distributive property. When you take b and you multiply b times m plus a, it gets distributed across both m and a. This is called the reverse distributive process, because we start with b being distributed to m and b being distributed to a. And here what we do is we pull b out of a, we pull b out of m, and put parentheses around m and a and say b is multiplied times m and a. Okay, so that's why we call it the reverse distributive process, because what we do is we pull b out of m and a, and then put parentheses around m and a, and then we say b times the quantity m plus a is the same as m times b and a times b. Okay, so if b were a binomial expression, so right here b is just a variable. But if b were an expression like x plus n, so if x plus n was multiplied by m, and if x plus n was multiplied by a, what we could do is pull x plus n out and have x plus n multiplied times n plus a. So you see that the reverse distributive process works whether you have a single term that's distributed across m and a, or if you have a larger term like a binomial term that's multiplied across m and a. What we can do is we can pull x plus n out of m and a and multiply it times m plus a. Okay, so this works the same way for what we are going to be, what our equations are eventually going to look like. Instead of having an m and a, we're going to have nx and h. And nx and h are both going to be multiplied by mx plus g and mx plus g here. And what we can do is pull out mx plus g so that mx plus g is multiplied by nx plus h. Okay? And that's how we're going to arrive at our solution. So again, I know that's a little confusing. You might have been able to follow, but what we're going to do next is use some numbers so that you'll see how this all works. The last thing that we typically do is we want to prove that our solution, or our factored solution, mx plus g times nx plus h is equal to our original quadratic function. And again, the way that you would do that is you multiply mx plus g times nx plus h. And if you do that, you'll get these numbers here. Again, it's hard to understand it because these are all variables. What we're about to do is show you what that looks like with numbers. So let's go see how this looks with numbers, so that hopefully that'll be a lot more helpful. What we had up here was just a general discussion. Let's come down and see what that looks like with numbers. Okay, so let's first look at what is a quadratic function when a is greater than 1. Okay, and we cannot factor out a GCF. Okay, so we have some examples here. Remember, the greatest common factor is a factor that is in front of x squared, and it's a factor such that when you take that number that's in front of x squared, and if you can divide it by each of the three terms evenly, then it's a greatest common factor. And if you look here, this equation is an equation that's an example of a greatest common factor, because this 3, we could actually, if you take this 3 out, you could actually take this 3 and divide it by each one of these terms, and it would divide evenly into these terms. So you could actually factor that 3 out and make x squared equal to 1 and solve it the way that we solved it in the past. The same thing here. 7 can go into 56, and 7 can go into 336. So therefore, this is also an equation where you can factor that 7 out, and we can solve it with one of the old methods. But as you can see here, this is 35. 35 cannot go evenly into 29, and 35 cannot go evenly into 6. So this is an example of a quadratic function where a is greater than 1, and we have to solve it using the methods that we just discussed above. Here we have 3, and 3 can actually go into 6, and 3 can go into 105. So this is an example of a quadratic function that we can solve with one of the previous methods. Here we see 14 cannot go into 23 evenly, and 14 cannot go into 3 evenly. Okay, if you divide 14 into either one of those, you get a decimal point and a remainder. So this is an example of a quadratic function that we would have to use this new method to solve. The same way here, 6 cannot go into 47 evenly, and 6 cannot go into 77 evenly. So again, we would have to factor this quadratic function using the new method. Okay, so I just wanted to show you some quadratic functions and how to tell whether or not the quadratic function is the type of function where a is going to be greater than 1, and we have to use the new method. So we're finally at the point where we're going to actually look at solving a problem where a is greater than 1, and we can't factor it away. So let's look at this example here. We have a problem, and remember, if a is greater than 1 and we want to find g and h, in order to find g and h, what we're going to do is have to multiply a times c to find out what g times h is. When a was equal to 1, we only looked at c. But since a is greater than 1, we're going to need to look at a times c equal to gh. And remember, for b, we still want b to equal g plus h. So let's look at this equation here. 6x squared plus 47x plus 77. Okay? So we want a g times h that is equal to a times c. And here we see a is 6, c is 77. So 6 times 77 is 462. So we need a g times h, or factors of g and h, that will equal 462. But we also need, at the same time, we need that g and h to be such that g plus h is equal to b. Okay, and we know here that b is equal to 47. So whatever our number is, we need our g plus h to equal 47, and we need our g times h to equal 462. Okay, so what we have to do is go to the quadratic function factoring worksheet to give us these values. Okay, and you can see here we found that G is equal to 14 and H is equal to 33. But let's actually go to the spreadsheet so we can show you how we arrived at those values. So what we're going to do, our A value is going to be 6, our B value is going to be 47, and our C value is going to be 77. Okay? And remember, we're going to need, instead of looking for C equal to 77, we're going to need to look for A times C, which equals 462 to find G and H. Okay, so let's go and do that. Again, A is 6, B is 47, and C is 77. So we go to our quadratic function spreadsheet, and we want to be in the first tab that says factor quadratic function. Okay, and if you have any numbers in here, you want to make sure they're deleted. So you touch it, delete, touch, delete, touch, delete, touch, delete. Okay, so the number we want to put in here now is 6. The number we want here is 47. And the number we want here is 77. I believe that's true. Let's go back and just check right quick. Yes, 6, 47, and 77. Okay. And now what we want to do is go to our down here to our tab and go to our second tab that says create factors. Okay. And if you notice what the spreadsheet has put up here, it says we're looking for A times C, which is 462. Okay, so the spreadsheet already recognized that since this was not equal to 1, instead of putting 77 there when A is equal to 1, it knows that when A is greater than 1, we actually want A times C, which is 462. So it actually puts 462 here. And remember, in the spreadsheet, you don't want to touch any boxes except yellow boxes. If you touch some of the other boxes and modify them, the spreadsheet won't work correctly, and you'll need me to give you a new spreadsheet. Okay? So remember, the rule is try to look for the number, the smallest number that will divide into whatever number we're dealing with evenly. And since this is an even number, we'll select 2. And again, we know that these two numbers sum to 462. These two numbers multiplied together are equal to 462, but we're looking for two numbers that sum to 47. See, because we want a B where G plus H equals 47. We want a G times H to equal C times A, which is 462. Okay? So here we have 231. So that's not an even number. Let's try 3. And we see 3 does divide by it evenly. This is not an even number, so we can't use 2. Let's try 3. You see here that's a decimal, so we know we can't use 3. It needs to be a number that divides evenly. Let's try 5. That's a decimal. We can't use that. Let's try 7. Okay, so we see 7 divides evenly. But what we see here is we don't get, it's still not equal to 47. And here we don't have any numbers that can divide into 11. And so we don't have any numbers that represent 47 here. Okay? So when you've tried this method where you use the smallest number possible, first, if that doesn't work, if that doesn't give you the number you're looking for, then what you need to do is try the largest number first. Try the largest, for the very first one, try the largest number first, and then go back to the smallest number. Okay? So we tried the largest number first, and then we're going to go back to the smallest number. So let's try 2. And see, here we go. So the numbers that we want are 14. So G equal 14 and h equals 33. As you can see, that's it gives us a 47, which is what we want here. B equals G plus H equals 47, and G times H equals 462. Okay, so we saw those numbers. Let's go back here. We saw that those numbers were G is equal to 14 and H is equal to 33. And that's what we got here. And so now what we're going to do is use those numbers again. Now that we have these numbers, what we had done previously, once we got a G and H, when we were using the old solutions, we were finished. We take the number for G and H, stick them in here, or stick them in here, and we're done. But with the new process, we don't do that. Once we find G and H, we're going to use this G and H to replace the value of Bx that we had in our original equation with the sum of Gx and Hx. So let's just see how we do that. So here we have our original equation, 6x squared plus 47x plus 77. But now what we're going to do is we're going to replace that 47x with the sum of Gx and Hx. Okay, so what we're going to do is we're going to say, instead of 47x, what we're going to do is put in our Gx, which is 14x, and Hx, which is 33x. Remember, G and H, G was 14, H is 33. So we're going to put an X on 14 and an X on 33, and we're just going to simply substitute those in for the 47. Now what you'll notice is if you sum up 14x and 33x, they're equal to 47x. Okay? But we need to split the equation up like this so that we can use the reverse distributive process to give us our answer. Okay? So the next step is, once we've taken the 47x and split it up into two numbers, and we get those two numbers from G and H. G is 14, so we're going to make it 14x. H is equal to 33, so we're going to make that 33x. So we just substitute those two for the 47x. And the reason that we're doing this is because we're going to need to rewrite or regroup this equation, put parentheses around two different parts of this equation so that we can regroup it and use the reverse distributive process to give us our answer. So let's go see how we do this. Okay, so what we do is we take this equation. Remember, we substituted for 47x, we substituted 14x and 33x. Okay, so I'm just bringing that down here. And now what we're going to do is we're going to group the first term, the gx. We're gonna group that with the 6x squared term. Okay, so we're going to take the 14x and we're going to group it with the 6x squared term. And so that's what we do here. Then the h term, the hx term, we're going to group with c, which is 33x. We're going to take the 33x and group it with c, which is 77. So that's what we do down here. Okay, so you can see we took the 14x and grouped it with 6x squared. We took the 33x and grouped it with 77. So in general, whenever we break up our equation into gx and hx, the gx term, which has to do which comes from the 14x, the gx is going to be grouped with the ax squared term. And so remember, g was 14. And so the gx is going to be grouped with the ax squared, which in this case is 6x squared. And the hx term is going to be grouped with c, which is, and h was 33, that's going to be grouped with 77. So you can see we sort of show you that rule right here. If you start with this equation here, ax squared plus gx plus hx plus c, we're going to group the gx term with the ax squared term. We're going to group the hx term with the c term. And that's what we did here. So the gx term, which was 14x, that gets grouped with the x squared term, which is 6x squared. The hx term, which is 33, remember we got h equals 33, that 33x is going to be grouped with the c term, and here c is 77, and so that's what we have there. Okay? So what we do is we bring those down here so that you can see that. We have 6x squared plus 14x. That's our first sort of binomial expression. And then we have 33x plus 77. Now the reason that we group them like this is because we want to pull a greatest common factor. We want to pull a greatest common factor from each of these expressions, which means we're going to be able to pull a number out of each of these expressions, here out of this first one, and we'll be able to pull a number out of this second one, such that what's left inside the parentheses will be the same. So that's the technique. That's why we're grouping these two expressions like this, is because what we want to eventually do is pull a factor out of each of the expressions in the parentheses, such that what's left inside the parentheses is the same. And so what you see here in the first parentheses, you can see we can pull a 2 and an x out of each term. If we pull 2 from the first term here, that's going to leave 7. If we pull 2x from the first term, that's going to leave 7. If we pull 2x from the first term, that's going to leave 3x. Okay? Similarly, with this expression here, we could pull out 11. If we pull out 11 from this term, you see we'll be left with 7. If we pull 11 from this term, we'll be left with 3x. Okay? And when we do this, now it makes it possible for us to actually use the reverse distributive method to actually come up with our factored solution. Okay, so let's look at that. But before we move on, let's just re-review how we pulled these numbers out. Okay, and what does that mean? What you want to do is look at each of these terms. Here you have a 6x squared. Here you have a 14x. So one of the things that you know is you can definitely pull out an x, because you have x here and you have x squared there. So if you pull an x out, it's going to leave you with no x here, and it's going to leave you with 1x here. You can also pull out the number 2, because 2 is a factor of 6 and 2 is a factor of 14. Okay, and the way that you know you can pull out a 2 is that if you divide each of these by 2, you get left with these numbers. 2 divided by 14 is 7. 2 divided by 6 is 3. So that's sort of what we call the greatest. You want to pull out the largest number that's common to all of these terms. That's why they call it the greatest common factor. So 2x is the greatest common factor for this binomial, because you can pull an x from this term and you can pull an x from this term. And when you pull an x from this term, it's going to leave you with a number here. When you pull an x from this term, it's going to leave you an x. When you pull a 2 from this term, it's going to leave you a 7. And when you pull a 2 from this term, it's going to leave you a 3. Now, there's no other numbers that you can pull from both of these terms that are in common. So that's as far as you can go. The same way here, you cannot pull an x from both of these terms because they both don't have an x. But you can pull 11. You can divide 11 into both of these numbers evenly. So you can pull 11 out. And if you pull 11 out, 11 divided by 77 is 7. 11 divided by 33 is 3. And one of the things that you notice is when you pull the greatest common factor from each of these expressions, the number left inside the parentheses is going to be the same. And that makes it possible for us to use the reverse distributive method to actually come up with our solution. So let's look at the reverse distributive method. Okay, so here you have a number m times b and another number a times b. So that b is multiplied by both m and a. And what that means then is that we can pull that b out of this expression and multiply it times m plus a. Okay? And so that's the reverse distributive method. If we have two numbers, m and a, that are multiplied by the same number, we can pull that number out and multiply it by the sum of those numbers. We can see that again here in the second example. We have m multiplied by x plus n, and we have a multiplied by x plus n. Well, what we could do is pull x plus n out and multiply x plus n times the quantity m plus a, just like we pulled b out and multiply b times the quantity m plus a. Well, this is the exact same thing that we have with our factors of our quadratic function. Here we have two numbers, 2x multiplied by 3x plus 7, and 3 multiplied by 3x plus 7. I'm sorry, I've got an error here. This should be 3x plus 7. 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 Okay? So again, if we have two numbers, 2x and 11, and if they're multiplied by the same thing, see, they're multiplied by 3x plus 7, 3x plus 7, and I brought this down here. You have two numbers, like 2x and 3 are like m and a, and 2x and 3 are both multiplied by 3x plus 7, just like m and a are multiplied by x plus n, and just like m and a are multiplied by b. What we can do is pull 3x plus 7 out and multiply it times the quantity 2x plus 3. Just like we could pull x plus n out and multiply it times the quantity of m plus a. Just like we can pull b out and multiply it times the quantity of m plus a. Okay? And this is our solution. So this is basically how we come up with the solution for a factored quadratic function when a is greater than 1. We have to basically rearrange our quadratic function. We get g and h, then we use g and h to split up bx, and then we rearrange that gx and hx and group them into two parentheses like we've done here. We factor out the greatest common factor, and when we factor out that greatest common factor, it's going to leave the same number inside the parentheses here. Then we can use the reverse distributive method to find out, to create two factors for our quadratic function. Okay? So that's basically how we do that. It sounds like it's sort of a long process, but I was going through quite a few steps here. It's the first time we've done it. When we go through this in class with some examples, it will be a lot shorter, but I wanted to go through a lot of detail here so that you could see the individual steps. When we go through it in class and we do a couple of problems, you'll probably see it a little better. Then once you've been in class, you may want to come back to this video and see how we step through this, and it should make sense then. Okay? Alright, hope this was helpful, and look forward to seeing you in class to discuss this. Alright, thank you. See you soon.